Hey Gideon.
Hey, hey Roger.
Okay.
Yes,
I was
can you hear
testing
me
to make
now?
sure you're back. Yeah, I can hear you. Yeah, perfect.
Perfect, perfect. Very good evening to you.
Good evening. Yeah, you want me to turn on the video or that's okay?
That's okay, as you wish, as you wish. So, we're going to start with some few announcements and like a safety moment and things like that. So,
And then we'll go.
yeah, then we shall invite you, read out your bio, and then invite you very well
Okay.
to join.
All right.
Yes. All right. Perfect. Thank you for being on the call with us. So it's a webinar format, and this is very good for the safety and everything of this event. Yeah. So the participants are streaming in as we have opened up the gates.
Hello, everyone.
Hello, Andrew. Hello, all.
Gideon,
Yeah. Yes. Yes, please. We can hear you loud and clear, Andrew. Please go ahead.
Just a second.
Yes, Andrew, we could see your screen before. Just reshare just once again.
Okay. Okay. Please kindly help me confirm if you can see my screen once again.
Yes, we can see your screen. Good evening.
Okay. Thank you, Comrade Gideon. Hello, everyone. Welcome to our webinar on innovative drilling strategies for the Tilenga project. My name is Andrew Kirunda, and I'm privileged to serve as the Young Professional Chairperson for the SPE Uganda Section Board, and I'll be your moderator today with our section chair, Mr. Gideon Chibirige. In our agenda, we shall begin with an opening prayer, have a safety moment, opening remarks, and an introduction of the guest speaker. We shall have our presentation, a Q&A session where we can ask our questions. And please feel free to submit your questions in the chat throughout the presentation. And finally, we shall have closing remarks from our section chairperson. So at this point in time, let's have an opening prayer from a volunteer on the call. Okay, Mr. Isaac Nsimenta, please lead us in a prayer. Thank you.
Hello, confirm that you can hear me.
Yes, Mr. Isaac, we can hear you loud and clear.
Yeah, good evening, everyone. Let's humble ourselves and pray. Father, we want to thank you for today. We want to thank you for this distinguished lecture that we are going to have. May you come and be with us as we share and, share the knowledge and the different ideas. Father, we want to thank you for everyone that has gathered here and everyone that is planning to, to join the lecture. May we be with us. May we be able to share the knowledge. May we be able to interact and be able to, see the value into this. And also, as we plan as SPE, may all the upcoming activities be according to your plan and how we want them to be. May we see excellence in all that we do, and each and everyone here, may we all, achieve what we want to achieve. I've prayed in the name of Jesus. Amen.
Thank you. Thank you, Mr. Isaac, for that wonderful prayer. Indeed, the Lord is going to be with us throughout our webinar. Next, we shall be having our safety moment from Mr. Gideon.
Yes, thank you very much, Andrew. Can you hear me?
Yes, Mr. Gideon, we can hear you loud and clear.
Perfect. So a very good evening to you all, our distinguished guests on this call, as well as our guest lecturer today, who is Roger. I think I've got the pronunciation correct. Tamdem Auguste. I think it's a very French pronunciation, so I hope I've got it correct. And yes, today's safety moment is about a healthy vision. So my name is Gideon Chibirige, and I am the section chair of SP Uganda section. And on this call, we are pleased to have some of our board members. We have our director Kato as well on the call, as well as all our guests who shall introduce at the end of this call. So today's safety moment is about healthy vision. And to start with some statistics, on average, workers like yourself and myself spend about 6 hours and 40 minutes per day on computer screens, which emit blue light. And this has an impact on our vision, because every time you look at the computer light, you get eye strain. And I think you'll bear me witness that everyone that has looked at a computer for a long time has got this kind of eye strain. And prolonged screen time can cause dry eyes, headaches, blurred vision, and even visual fatigue. So here are some tips for maintaining healthy vision as we work and to keep your eyes healthy and young for as long as you can. Number one, follow the 20-20-20 rule. Every 20 minutes, look at something 20 feet away for at least 20 seconds. That's a rule you must follow, and it's recommended by doctors and professionals alike. The second is adjust your screen settings. In other words, the brightness of your screen should match your surroundings. So don't have too little light, or you'll be squinting your eyes, or too much light. The third is increase the text size to reduce eye strain. And fourth, maintain proper distance. In other words, keep your screen about an arm's length away. Don't be too close to your screen. Position your screen so that your eyes are level with the top of the monitor. Then the fourth category is about proper lighting. Avoid glare by using blinds or curtains. And also this might entail using a desk lamp with some shade to direct the light away from your screen. So take note that we shouldn't be, if we want to live long and to have healthy eyes, we shouldn't spend too much time on screens and smartphones. So because of that, we're going to keep this lecture very, very timely. Finally, consult professionals, visit an eye care professional for regular checkups. Thank you very much. That's a safety moment for this evening. Over to you, Andrew.
Thank you, thank you, thank you so much, Mr. Gideon, for that very wonderful safety moment, coming in very handy for our online webinar we are having. So next, once again, our topic today will focus on the innovative drilling strategies for the Tilenga project. We are excited to explore the cutting-edge techniques and strategies that are shaping the future of the drilling in the Tilenga project. This initiative is not just about technology, but rather it represents a significant advancement in our approach to energy extraction and sustainability. Before we dive into the presentation, I would like to introduce our esteemed speaker, Rogel Augustin Tandem, a senior drilling engineer with 29 years of industry experience. Roger is a dedicated, instructive, and meticulous senior drilling and workover engineer with extensive experience in offshore and onshore, ERD, high pressure, high temperature drilling engineering, directional drilling, wellbore construction across Africa, Middle East, USA, and Asia, working with various multinationals as summarized. And today, he brings his experience in well engineering construction to share with us. Let's get started. I'll now hand it over to our senior engineer, Rogel Augustin Tandem.
Yeah, good afternoon, everyone. I hope you can hear me.
Yes, we can hear you loud and clear.
Okay, thank you very much, Andrew, for the introduction and then for giving me the floor. I will now share my slides. If you can see, let me know.
Okay. Yes, we can see your slides. Perhaps you could put them in presentation view mode. Perfect.
Okay. So I will start my slide with a safety moment also, which is very relevant to the subject we are discussing today, which is directional drilling. So this safety moment is about a well collision case study that happened somewhere in the world. So what happened is, so a well named C1, top hole was abandoned because they had a lot of issues, problem while drilling. So they abandoned the well and then they decided to respot the well just next to it. And then while responding, they actually enter into a collision with an existing well that was producing. So they perforated the 13-395A casing, as you can see on the schematic on the right. So, what to learn from this is, again, we're in an industry where we tend to be always trying to make things, fast because we're trying to save time and money. So in this case, they responded the well, and then they forgot was one of the most important things, which is to reevaluate the anti-collision. So, and then they assume that the CP drill, the 23-inch hole will be vertical. So if you're drilling vertically, then of course, you are not going towards a different well. But in this case, while they were drilling, not monitoring, they got some deviation, and then that's where they were getting into a close proximity and then end up drilling into another well with the existing well with a 5.5-inch tubing. So if you look at a lot of things that were missed, so there was no anti-collision follow-up by the company drill engineer. Assumption that you have the well is vertical. So again, in the drill industry, we no longer assume, you survey and then you know where you are and then you define what's the cause of action. So what to learn from this is, a lot of rules of the company were broken, anti-collision rule. You don't drill a well if you have not done the assessment of how that well would be compared to the existing wells. And then define a survey plan to make sure that there's no, you don't get into the close proximity of that well. And again, if you are changing, like this well was supposed to be C1, when you go to C, when you change it to C2, you need to do a management or change, and then do a proper risk assessment to capture all the risks associated with the new well that you are going to drill, which wasn't done in this case. So there was no MOC process in place, and then they didn't comply to the rules and regulations. So yeah. So again, just to show us that if we drop the ball anytime, it could be very costly, for the company, for the reputation, or for the whole project itself. Imagine a well like this, when you collide and then you start getting gas into the well, you could get into it could turn into a fire, it could turn to anything. So imagine having, something similar in Uganda. That would be probably, a very detrimental for the company reputation and then for the country. So just to highlight that, what we do is very important, and then we need to pay attention to every single detail to avoid having a situation like this to ever happen again. So, yeah. Okay, so moving on. So today I will try to go through 3 different topics, which is just to show you the well type and trajectory that we have in Tilenga and the different well architecture, and then go through the directional drilling strategy that we go about delivering those wells, and then the wellbore survey. Now, for the reason that I mentioned earlier, the survey is very important to, for collision, or also for ensuring that we are actually placing our wells, within the reservoir where we think we are going to place it. And then we'll finish with Q&A, the session with Q&A. So the typical trajectory, stop me if I'm going too fast. I have a tendency to speak a little bit faster sometimes. So if I'm going too fast, please stop me, and then I would slow down. Yeah. Okay, so the typical trajectory that we have few wells which are going to be vertical. So typically they are reference wells. On each of the part, we drill what we call a reference well, which is drilled to acquire a little bit more information about the part itself that we're going to be drilling. So either they are vertical or they are just slightly deviated, and then we drill 1 reference well per part. And there's few wells which are 2Ds, like just slant with up to 200-meter drain. Now, the majority of the well will fall within the last 2 categories, the horizontal 2Ds and horizontal 3Ds. So, and then for this, the 2D wells and 3D wells, we have 2 different patterns. We have what we call the star pattern, which is what you see on the top, on this top chart, where the wells goes like in star. And then we have the second one, which is the comb pattern. So they are 3D, so they go out and then they kind of align again, where you have the injector and producer almost parallel. So the drain length would vary from, again, like I said, from 250 generally to up to 1,000. The longest drain we are planning for is around 1,000. So the casing issue, the typical architecture is we have a 1858 in CP, which is driven, which is cemented in place by the construction before the rig even comes, and typically set around 38 meters MD or TVD, because it's still vertical. And then we drill the top hole section in 14 3/4 inch and set the 10 3/4 inch surface casing, which main role this first casing is to protect the aquifer. So we drill the top hole with water-based mud, and then we set this casing to make sure that before we change the mud to the next, which is the SBM, that we have covered all the aquifer water levels, so we don't contaminate any of the water table with oil-based mud. And then we drill the intermediate, our intermediate section in 978, and then set the 758 casing, typically landing on top of the reservoir itself that we are planning to drill into. So once we set the 758, then we drill the open hole to TD, and then we complete with some sand screens. So that's typical architecture of a typical well in Tilenga. So any question on that before I move on?
We do not have any questions so far. We do not have any questions so far, so we can move on.
All right. So now, in terms of the strategy to try to achieve this, so we have several challenges. So the first challenge is that the target in Tilenga are very shallow. The shallowest is around 400 meters TVD. So when it means shallow, means you don't have you don't have enough vertical depth to be able to have all the weight you need to apply weight on bed or to push the casing down or to push the compression down. So that's one of the biggest that Tilenga trajectory would face, that the TVDs are very shallow. So most of the wells end up falling into the category of ERD wells. The ERD is the departure versus TVD ratio. So if you look here on the map, if you look here on the map that I'm showing, so this is where most of the Tilenga wells would fall. Oh, sorry, let me go back. Sorry. Okay, so this is where the out of the 400 and something wells, 178 fall within the category of ERD, which is a ERD ratio of more than 2, right? So you might say, okay, the wish farm wells go 40 kilometers. That's why they are ERD. But here we go 1,800 or 2,000. But because the TVD is so shallow, they are falling within that category. So they are very long, extended reach wells and very unconsolidated formation, because you don't have the compaction that it takes when you are deeper. So we are very shallow, very unconsolidated. So the first challenge was to be able to confirm that we can deliver a 5 degree per 30 meter kickoff. All right. So at the kickoff point, so because you have a pad design, so you have to go from the pad to the target, and then reach the target. And most of the time, in less than 400 meters, you need to be at almost 90 degrees. So it requires very high build. So we typically design the well where we have the build section, then we have the slant section, and then we have the final build to land in the reservoir that you can see here. Now, the slant section are typically designed for ESP, for the producer where you need to place an ESP, and there's a constraint on the ESP placement where you need to have a perfect, almost no dogleg for the pump to operate. If there's any dogleg, then the life of the pump would reduce drastically, and then you might end up having a premature failure of the pump. So this is one of the concerns where we definitely need to have an ESP section, where we're going to set the pump, and that ESP has to be set at a certain distance from the casing shoe where the suction will be. If you set it too far from it, then the pump efficiency also will be affected. So it's very critical to make sure that we are setting that ESP within that section in the 978. So again, like I mentioned, 14 3/4, we kick off shallow just to be able to get some departure from the pad. But we also have to manage the anti-collision. Like as you can see, the top hole is very crowded. I mean, you have a pad of 24 wells within the distance from slot is 7.5 meters. So at the surface, all the wells are 7.5 meters apart. But you need to make sure that you are not creating a collision between them when you are drilling, and also a collision with existing wells. There's some appraisal wells that were drilled before, so you'll see on some of the slides. So we have to make sure that we are not colliding with the appraisal well. Yeah. So on the 978 section, then we achieve most of the time we do the majority of directional work, which is to build and then probably turn if required to land on top of the reservoir. Then we have this provision for the slant section. But we also have a challenge, which is to make sure that we can run the 758 casing. So you need to optimize your trajectory to make sure that the casing would be able to go all the way to the bottom. If you don't have weight to push the casing to the bottom, then you can drill to 2,000 meters. And if your casing cannot go down, then your well is compromised. So that's one of the things we need to make sure that on the trajectory, we are optimizing to be able to have the 758 casing go all the way to bottom. So we in the design phase, you have to calculate what will be the torque and drag and the friction factor that would confirm that at the worst case scenario with the current data that we have from Tilenga, that your casing will be able to go all the way to bottom. If not, then you have to change the trajectory to achieve that goal. Yeah, it's very important, because if you drill and then you cannot case it, then the well is not usable. And the drain section, which is the way we'll be producing or injecting, is usually less directional work because we already set the 75 on top of the reservoir. So typically we do a slant in the reservoir or we turn very little, whenever we can. So most of the wells are designed to be just slant with some geosteering for the GSR to place the drain in the optimal or the sand facies that they think would be the best for that reservoir itself. Yeah. So again, the reservoir will be very high angle, but we need to make sure that also we can run the completion because most of those wells will be completed with running sand screens. So that's one of the limitations of how far you can drill because you have to run the 4.5 inch by 3.5 inch screen, which are very flexible and small. If there's no way to push it down, then if the screen do not go all the way to bottom, that means you are not going to produce or inject your whole reservoir. There's no point to drill if you cannot produce, right? So that's one of the limitations also, and we need to make sure that our trajectory are designed so that we can run the completion all the way to bottom, or to run all the section that we drill. So. Any question on this?
No questions yet.
Okay.
We can still continue.
Okay, so to be able to achieve these objectives, so we had to do a lot of studies for all the 3-hole section. So the first one was for the 14.75 inch section. So there was study performed by Total and then some directional drilling contractors to design what would be the best BHA strategy to be able to kick off as early as possible and then achieve that because once you kick off earlier, then you are able to separate the wells and then you solve the collision concern that you have. So kick off as early as possible and achieve reasonable dog legs before you go to the intermediate section. So if you see on the on the right, so study were done about using what bend angle will be used on the motor to be able to achieve the target plan at that time was 5 degrees per 30 meters in sliding. And if you see, depending on the hole size that you get, typically when you are drilling 14.75, you get some hole enlargement. So you might be drilling 14.75, but your hole size itself might be 16 inch or 17 inch. So you need to do simulation, assuming that the hole could be slightly larger than what you think it is, right? So that's why the simulation here is using the overgauge. So for example, if you look at the different chart, they correspond to different overgauge that you have while drilling. And if you use a 1.5 degree bend angle, the study were showing that if you have hole size of more than, if you have an overgauge of more than 7/16 inch, then you are not going to be able to achieve it. Or even half an inch, you are not going to be able to achieve 5 degrees per 30. So we did again simulation, increasing the bend angle to 1.75, and then now it showed that, okay, even if you have half-inch overgauge, which is very typical, when you drill a 14.75 inch section, you are most likely to have a half an inch or 1 inch overgauge, because you have very soft formation, and then you when you get formation washing out, then you create a bigger hole than the bit is actually drilling. So that's why we had to go with the highest bend angle that you can rotate, which is 1.75. Now, for the motor, you can go higher than that. You can go 1.83, 2.18, 2.38 even. But those with those bend angle, you cannot rotate. So that would mean you will only slide. But if you slide, for example, let's take a case of 2.38. If you slide 2.38 bend angle, the dogleg that you get would be more than what you need because you cannot control it. Typically on the motor, you slide and then you rotate. You slide a percentage, rotate a percentage to get the dogleg you need. If you go with a very high bend, like 2.38, You will only be able to slide. So that will mean you slide, you get your angle, and then you have to pull out because you cannot rotate it, and then you cannot just continue to slide, right? So we had to settle with the best, the biggest bend angle, which is 1.78, that allow a certain rotation on the string, which is 20 to 30 RPM. It's not much, but at least it allows you to be able to deliver gradual dogleg without having to pull out and then change the bend angle. Yeah. So if you look, for example, if you heard the story about the short radius drill in the US, so the short radius, they drill with the motor with those high bend angle, but they slide all the way until they land, and then they pull out to dial the motor back to a different setting that they can rotate. Yeah. So again, so one of the things that affects the performance of the steering motor and this top hole would be the washout. So how do we mitigate having those washout? Is to control the flow rate, especially when you are exiting the CP. You don't want to wash your CP away because the CP is the one that supports the whole structure where the BOP and everything will be put on. So if you wash your CP away, then there's a risk of your CP, settling down after moving, and then you can start getting cracks and then losses, on the interface between the CP and the formation, and then you get fluid back to surface and so on. Yeah. So we need to make sure that we don't wash the CP shoe, and then we drill few meters before we increase the flow, just to make sure that integrity of the CP is very good. And while drilling, we avoid to circulate a long time in the same position of the BHA, because if you stay at the same position, especially in the sun, and then you circulate, then with the jet that the fluid is going from the bed, you'll be washing the formation away, and then when you wash it, it's not homogeneous, so you create some washout, and that will affect also your dogleg capability of your BHA and overall your ability to deliver that trajectory. Yeah. And the third point is, again, hole cleaning mitigation, because on this top hole, again, we are using water-based mud. There's a lot of shell, so we need to make sure that the mud had some very good inhibition. Otherwise, you get some gumbo, which are clay that will absorb the water, and then they will form as sticky clay, and then they will, cause a lot of problem either in the surface equipment or downhole. So the hole cleaning is a very important part of this strategy for the top hole, making sure that we pump the pill to, we clean, we drill, we clean, pump pills before we continue, right? So any question on this section?
Yes, so far we have one question from Mr. Ramos. His question goes, why do we need an ESP for the oil producer wells? That's his question.
Okay, I'll get to that, but I can answer that right now. So the oil that we drill in Tilenga is very viscous. So the oil would not come, it doesn't flow by itself. Like if you look at different locations like US, where the crude oil or Brent that they produce in the North Sea would flow by itself because of the viscosity. They're very good quality. But the one that we're producing here is very heavy oil. So you need to pump it out. And not only you need to pump it, but you need to be able to inject water in the water zone to push it up and then pump it out. So it's a combination. So the production we do in Tilenga would be a combination of water injection to support the pressure regime and also ESP to pump the oil out. Yeah. If you had a lighter oil, then you could have produced it with gas lift just by injecting gas in the column, and then it will lift it up. But it's too heavy for the gas lift, so you have to mechanically pull the oil to surface, whether it's ESP or PCP. So what the study done for this project was shown that ESP was the best design for the flow rate and the production target for the Tilenga. Yeah.
Okay, thank you. We have a couple of other questions, but most of them are out of this particular section. So please keep on sending your questions. We shall address all of them at the end of the presentation. Please go on, Engineer Roger.
Okay, so now moving on to the intermediate section. So again, we have similar challenge. So a lot of studies were performed to design what will be the best BHA that we can use to achieve high dogleg and also to be able to have a smooth trajectory for the same reason that I've shown earlier. So we decided to go with the RSS, which is one of the best RSS we have in the market, capable of delivering 6 degrees per 30 meters. So that means you could go from vertical to horizontal in if you multiply by 10 in 500 in 500 meters typically, right? So if you do just continuous rotation while drilling and then putting 100% steerability, then you are able to get from vertical to horizontal in 500 meters. So again, to be able to decide what would be the RSS that would achieve the dock leg requirement of the Tilenga project, like if just to give you an idea, so the typical dock leg for this whole size around in Africa, like in Angola, is 4.5. And so on. So you see, we are taking it up because we are very shallow. No, you have to get to that angle very quick, right? So that was one of the concerns where we needed to make sure that we could achieve a high angle. So if you look at this chart in the right, so we had to do studies to confirm that, again, based on the steering percentage and a hole being slightly over gauge, what would be the maximum dock leg you can achieve? And the steering here, this chart here is showing that with 100%, which is the blue curve, with 100% of steering and the 1/4 inch over gauge, which is the typical over gauge that we get in this whole size, then you can deliver up to 12 degrees per 30 meters, which in fact, in competent shell, you are able to do that, right? So the studies gave us enough comfort that using this RSS, we will be able to achieve our 6 degrees per 30 with 65% activation. You don't want to plan to be at 100% all the time, because as soon as you cannot, for any reason, you cannot achieve on one survey, you cannot achieve that, then you cannot go to 110%, right? So as a design criteria, most of the time you would like your BHA to be able to achieve your dock leg with 60 to 65%. So when you get into a hole that's more over gauge or loose sand, then you can increase it to 80, 90, and then still achieve. So that's the criteria behind selecting the tool that will give you the required dock leg. And if you see now in the actual case, there was no anticipation, but in the loose sand, most of the time we have to go to 100% activation to be able to get some dock leg, right? So again, this tool, so in a competent shell, at 100%, you can get 12 degrees. In a loose sand, at 100%, sometimes you get 1 degree. So it just show you how the different formation type would affect the reaction of your RSS, right? So at the beginning, so we use this, and then as we start drilling, we have lesson learned on which type of formation, which loose sand is the one giving us a problem, and then we adapted our design to make sure that we don't plan too aggressive in the loose sand, or that we change the parameter while drilling those loose sand. Yeah. So I will come back to that. I'll come back to that on the next slide. So yeah. So again, so one of the things to do is, again, to mitigate the hole being too big. You know, if the hole is too big for the bit we are drilling, then the tendency for the BHA will be to stay on the low side, and then you're not going to build, because it's, again, the gravity will be pulling everything on the low side. So if you are washing, and then the BHA will just follow and then stay on the low side, it won't go up to whatever, to 90 degrees as you are planning to go. Yeah. So same thing, we need to use the oil-based mud or synthetic based mud to avoid having some shale reactivity, you know, because now we are drilling horizontal and a very long section. If on top of that you have shale closing on you, then it's going to be very difficult to do. So that's why we use synthetic based mud. And then we have to control the flow rate to avoid, first of all, washing the formation, and second, to make sure that we have steerability from the BHA. So this RSS is what we call is a hybrid, which is point and push to the bit. So it uses the flow to deflect the steering unit to point up. So it requires a certain pressure drop across the steering unit to push to be able to deflect. So that pressure range is very limited. So you have to be within that range. Otherwise, you are not pushing enough. So if you pump too much, you wash. If you don't pump enough, you are not pushing. So you guys understand what's the challenge here. So you need to make sure that the flow is within a certain range to be able to push enough and then not wash. So we had to work on the bit optimization, especially the nozzles, to make sure that the nozzles are oriented downwards, not side, because on the side, they will be jetting the formation and then creating washout, but they are oriented downward to clean the cuttings ahead of the bit. Yeah. And then again, same thing, we need to avoid the long circulation in sand. So if you look, so most of the time when we are drilling the 978 section, if for any reason we need to circulate to reduce the ECD or to work a pack off or for any well status event, then we try to circulate when we are in shell. Because if you do that in sand, you're going to create a big pocket and then you're going to wash out and then your BHA will fall in that pocket. Yeah. So again, so a very drilling the long ERG, one of the most difficult part of the ERG is cleaning the cuttings, right? So you drill the hole and then the cuttings stay on the low side because that's the natural tendency. The gravity will pull the cuttings to be below the BHA. So you drill, but you need to make sure that while drilling, you are cleaning to the maximum. Otherwise, when you finish drilling, you cannot pull out because the cuttings would hold the BHA. You know, if you have so much cutting in the hole, you cannot pull out. And for you to run your casing or your compression, you need to have cleaned at least a certain percentage, which is at least 80 to 85% of the cuttings out of the hole before you can run anything back in. So hole cleaning is one of the most critical part for the ERGs. And there's a lot of parameters that come into play, which is the RPM, the mud rheology, to make sure that the cutting lifting efficiency is very high. And then you are, whatever you are drilling, you're actually sending it out to the surface. And then once you finish that, then you clean the cutting beds that remain in the hole, laying on the low side on the way out, and so on. Yeah. So we had to develop a strategy that we're still developing, we're still working on it, because the more we drill, then the more we are facing different challenges with different field and different parts. So that is an ongoing process that's been implemented now. Yeah. So again, some of the improvement that we are looking at is trying to design a PDC bit which is not aggressive. Like I mentioned, when you get into the sand, we can drill even 200 meters per hour because the sand are so loose that just the pumping, the sand move away. But because you are pumping and the sand is moving away, it's difficult for you to maintain, to build or turn because the BHA is just following. So we are working with the contractor, directional drilling contractor, to look at the different design of a PDC bit that would not wash that much, and then that will require a little bit, because to achieve any dock leg, you need to put weight to have the deflection, right? So that's still work in progress. Any question on this slide before I move to the next one?
No question. We can continue.
Okay, so the last section, which is the reservoir section, again, so we went with the same strategy to do the studies to see what would be the best best tool. Now, at this stage, you see, we no longer talk about the motor BHA, because a motor BHA, you wouldn't be able to get to transmit weight to drill with a motor at this depth, right? So you definitely need something that you are going to rotate and then deflect at the same time. So the motor is already out of the range in this when we get to this hole size. So definitely you have to go with the RSS, and we had to look at what RSS would be able to give us enough dock leg to be able to build in the sand. Now we know that we have very unconsolidated formation, but we need to be able to build in sand and then get some place our reservoir where we want to be. So again, studies you do it with you have to set a compaction, and then so if you go to a very competent formation with this whole side, you can still achieve 12. But we are in sand, very loose sand, you will be limited to around 4 degree dogleg with 100% activation in the loose sand. Yeah. So again, so same thing, we need to do the same mitigation we are doing for the other hole size, avoid having big hole by washing the formation. So using the synthetic base mud and controlling the drilling flow, and then avoiding circulation in the loose sand. So those are the mitigation that we usually do for all these, for the last 2 sections, to be able to get to the, to be able to drill and then pull out to run either the casing or the completion. Yeah. Okay, now, so since so far we've been just talking about the BHA itself, how to drill. Now, if you drill, you need to know exactly where you are. Now, it becomes more critical when you have wells which are very close to each other, right? So you cannot afford, like I mentioned, the top holes are 7.5 meters apart from each other. Now, when you take a survey, we have what we call the ellipse of uncertainty, which is the error on the measurement that makes it that if you think you are at the center, you might not be exactly at the center. You might be, plus or minus to the left, to the right, or up and down. So that's what defines what we call the ellipse of uncertainty. So you have to make sure that when you get to that 1,800 meters, that you are within the ellipse of uncertainty defined by the RGS, by the GSR, as that's the target where they want to be. So it's very important to do a proper wellbore surveying, not only for anti-collision, but also for target sizing. So if I want to place my drain at XY coordinate plus or minus 10 meters, I need to make sure that when I get to that XY coordinate, that I've surveyed to confirm that I'm within the 10 meters radius, or 10 meters rectangle, or whatever you define your target to be. Yeah. So it's very important to have the accurate surveying for that. And also there's a risk for the deeper section to have a magnetization of the drilling of drill string or merge. So you need to make sure that you are surveying it's not affected by that magnetization. We have not seen that yet in the Tilenga so far because we recycled the mud, so that's not a big challenge. So the big objective that we have now for the wellbore survey is the accurate wellbore positioning and the collision avoidance. Like you can see here on the right, so we have, for example, when you see here, it represents this cone that you see is the cone in which the well would be placed. So you could be either on the left, on the right, or on the middle of it. So that's why it's important that 2 cones do not touch, because if the 2 cones are touching, it means you have a risk of collision. Right. So that's, in very simple word, how you look for and how you avoid anti-collision. If I'm drilling well A and then well B, I make sure that the cones between the well A and well B don't touch. And to be on the safe side, the company has designed what we call the minimum separation distance. So that means wherever I am, I make sure that there's a minimum distance between the 2 wells. So that minimum separation distance and clearance factor are the 2 main components that we use for making sure that we design our survey program to avoid anti-collision. Yeah. So at the beginning of the project, we had to look at 2 different things. What's the collision risk when we have magnetic interference? Or what's the collision risk when we don't have magnetic interference? So when we don't have magnetic interference, it's typically the reference well. Being the first well drilled on the path, we don't have any other wells around it. So typically,
Hello.
Hello.
Yes, I think our presenter is having some bit of technicalities on his side. Just give him a few. Yes, Engineer Roger, you're back.
yes. Okay, sorry.
We lost you a couple of few seconds ago, so perhaps maybe you would re-echo on this particular slide.
On this slide, okay.
Yes, thank you.
Okay, yes, so I was saying that for the top hole, we have two different scenarios. So we have the scenario where you have magnetic interference from the nearby wells, and then you have a scenario where you don't have any magnetic interference. So typically, when I'm drilling the reference well, which is the first well on the pad, being the first well and the only well, there's no other well around it to create the source of magnetic interference. So we use MWD and SAC for the surveying, right? Now, once you start drilling the other top holes, then the more top hole you put, then the more source of magnetic interference you get when you are drilling the next one. So in that one, we opted to go with the gyro while drilling. The gyro means it's not affected by any magnetic interference. So you can take a good survey even inside the casing itself. Right. So that's the strategy that we adopted. So typically on Tilenga, the first well, the reference well will be drilled with MWD only, MWD and SAC. And then the rest of the well will be drilled using GWD, gyro while drilling. So, and then we always make sure that we adjust the trajectory, the top hole trajectory, so no wells come into a close proximity of another well. With the company rule, the total rule is the MSD, which is the minimum separation distance between the ellipse, should not be less than 1.5 meters. Or the clearance factor should not be less than 1.5 meters. So if you cannot abide by this rule, then you need to change your trajectory. Right? If for some reason you cannot change the trajectory, and then you need a derogation that you have to send to HQ and so on, right? You need a derogation that will show that you are accepting that risk, but yet all the mitigation are in place for you not to collide. So if you cannot prove that the mitigation for not colliding are in place, you are never going to get a derogation. So typically the derogation would be when the MSD would go less than 1.5, but the clearance factor will still be more than 1. We show that, okay, yes, you are very close to it, but you are not touching it. Right? So that's typically what you get when you are drilling the top hole. So like I said, so the GWD plus SAC, and then we did a lot of, we are doing analysis between the GWD data and the MW data to see what's the impact of the magnetic interference from the nearby casing. And so far it's showing that yes, as soon as you start having the nearby 10 3/4, then even a well that's 40 meters from you could see some bad survey, you know, as you drill. Yeah. So that's why we are keeping the GWD in the string so far. Yeah. So when we get to the deep section, again, so although you still have a collision avoidance issue, but now you no longer had the magnetic interference from nearby well, because the intermediate section, you already have enough separation from the nearby casing, you know, because like you see in this case, you see the intermediate section will be stopping at the blue, so you already have enough separation. So we use the MWD, and then we have we apply a correction, what we call it IFI, infield referencing. So for those who are not familiar, the infield referencing is, so there was a data acquired by the national drilling contractor. So they came here and they acquired data of the Tilenga magnetic field. And then based on that data, they can apply a correction on the azimuth to make it look like, to make it very close to the quality that have been delivered by the gyro, basically. And then to validate that model, we have to do some by running gyro on selected well, just to make sure that, okay, on well A, we have the IFR model, and then on the same well, which shows 10 wells on the Tilenga, and which are spread across the field. So far, we did 3, where we run the gyro, and then we make sure that the ellipse of uncertainty that we are getting from the gyro is very close to the one we are getting from the IFR. So that gives us confidence that we can use the IFR model for well positioning, as it was shown on the studies. Yeah. And then so far we've been able to cross an existing well with a center to center as low as 21 meters. So imagine you're 1,000 meters and then you have a well that's theoretically 21 meters above you, but that 21 meters is just center to center. So the MSD, which is the minimum separation distance between the two ellipses, was around 4.5 meters, and we managed to do it. So that's why it's very important to make sure that you have an accurate survey program that, based on the objective you're trying to achieve. So if you see here on the right, what we call the target, to reach a certain target. So the green, it's, for example, what the GSR will give us as a target. So the GSR will probably want to say, okay, the hill, you want to land the well at this point, plus or minus 15 meters. So minus 15 to the left, minus 15 to the right, and then on the top 5 meters or the bottom 5 meters. But the driller's target has to be smaller than that because the geologist's target is a point. The driller's target has to take into account the EUU, the ellipse of uncertainty. So that's why you see the black that you see in the middle is now the driller's target, ensuring that wherever you are within this driller's target, with the ellipse, when you add the ellipse on uncertainty, you still remain inside the geologist target, right? So that's what you see, people will refer to as driller target versus geology target. So the driller's target is always narrower compared to what the geologist allow as target, just to ensure that when the driller is in his target, then given the ellipse of uncertainty, we are within the geologist target, right? So a lot of studies were done to determine what tool we are going to use. So we did some check with just MWD, IFR plus SAC. And if you see the uncertainty, typically at landing is around 11.5 meters. So we say, no, 11.5 is still too high. It's high, we need to reduce it. So that's why we do this. So if you look at GWD, gyro at TD, which is the best, if you run the gyro at TD, you're going to get an uncertainty of 7 meters on each point. But if you look at the cost implication of that, then it's a little bit higher compared to what you are gaining if you run only MWD, SAC plus IFR plus MSA. So this is what we chose, right? So we end up with 11. Now we could have gone with a GWD 90, but it wasn't available, and the reduction was not a great impact. You go from 58% to 68% only. So. Yeah. So again, so these are the studies that you do prior to starting a project to take which solution is economically and then technically passing, right? So it shows you that, okay, MWD, SAC plus IFR plus MSA is giving you a good enough position to be able to define your target. So in conclusion for this, so we are able to achieve, we successfully drill, we are already 78 wells so far, and more than 100 kilometers on 4 well pads. We just finished the 4th one. And in terms of trajectory execution, we achieved 100% within the drilling tunnel. So that means there's no well where we have said we.
Hello, Engineer Roger. I think
Yes.
we've.
You lost me again. Hello? Hello?
No, we can hear you. I think, yes, please,
okay.
please go ahead. Yes.
Yes. So I was saying that, we are able to achieve, to drill all the wells so far with 100% on trajectory execution. We show that our strategy is working. We are not, we've drilled well very in close proximity to existing appraisal well. Like I said, we drill a well past 2 of the well where we were below by 4.5 meters. So successfully, and then we place the reservoir where we wanted to place. Yeah. So we mitigate the project challenge, because one of the big challenges at the beginning of the project was, are we going to be able to kick off earlier and then deliver the dogleg? So which we have done consistently. And then now we have in our pocket that we can kick off as early as 60 meters. So when we have a challenging trajectory, we kick off very early to get some departure. So we drill all these wells without having any collision risk. We haven't done any derogation. So that means we have been drilling in the drilling tunnel without getting too close to a well, to another well. We still monitor, when we are less than 5 meter MSD, but we haven't been in a situation where we have an anti-collision risk. Yeah. And then we were able to accurately place all our well as per the GSR recommendation. Yeah. So this is just a summary of the BHA. So 14 and 3/4 again is steerable mud motors, and both 9, 7, and 6-inch are RSS BHA with what we call the power draft archer, which is a combination of point and push to the bit. So it's what we call a hybrid. So it uses hydraulic forces internally to push and deflect. So that's why it's a push and point. So it's both. Yeah. Okay. So that the end of our presentation. We are now open to any questions.
Oh, thank you so much, Engineer Rogel, for that very, very wonderful and powerful presentation on our topic. We've got quite a number of questions in the chat. I think we shall begin with these right away. The very first question that was answered, the second question, I'll read it out. The question is, if the several wells are drilled on a single well pad, given that they are highly deviated at certain angles, how is this achieved? Because I see drilled pipes are usually straight. Maybe you can take on that very briefly. Move to the next one.
Okay, so let me go to, okay. So if you look, for example, on this chart, so this is what we call a plan view, right? So this is what you will see if you are looking at the surface. That's in which direction they are going, right? So there's a plan view, and then there's what we call a vertical section view. This is what you look if you are cutting the formation and looking from the side. So let me show you, for example, I think I have it in this chart. No, I don't have it on this chart, but I will quickly show you one plan view so you see the difference. So typically, when you see from the surface, there are the different TVD, right? They are the different, as you go down, the wells are different depth. So this is what you see, what it will look like if you are looking from it from the top. So they are not touching actually. Even the one you see here that, so for example, if you see these two wells here, it looks like they are crossing, right? But in fact, they are crossing at different depth TVD. So one is on top of it. But if you look from top, if you are looking from the top view, then you see it as if they are touching, but they are not touching actually. Did that make sense?
Yes, thank you. Thank you so much for that one. The second question is from Dina. Dina asks, how do you manage the whole cleaning with the fact that you still have to keep note of the flow rate?
Correct. So again, so that's a very sensitive topic. So because for the whole cleaning, yes. So we need to, the whole cleaning is a factor of methodology. So first of all, we need to make sure that the methodology are perfect. So, for example, for the 970 section, you want your methodology to be as high as possible to make sure that you are lifting the cuttings, right? But again, the high methodology would also mean high ECD. So you have an ECD window you need to play with. So you want them to be as high as possible, not out of the window. It still have to be within a certain range. You want your flow rate to be as high as possible. But like I mentioned, the flow rate should be as high as possible. But if you pump too much, then you're watching the formation. So you have a window. So it's playing with all these parameters that you design your whole cleaning strategy. And then the RPM, of course, the RPM needs to be high enough to be able to move the cuttings in the hole as you are drilling. Because if you are not rotating enough, then the cotton will settle on the low side. So you need to high rotation to move the cottons and then put them back in the upper layer where the mud is flowing, and then where the cotton will be lifted up, right? So yes, so playing with the methodology, RPM, flow rate, it's what you define your whole cleaning strategy. Yeah.
Thank you for that one. So we shall have a balance. We still have quite a number of questions in the chat, but let's have a few from active speakers online. Mr. Wycliffe, please go ahead to unmute your mic and ask your question. Let us keep it very brief and summarized.
Yes, thank you, Roger, for that presentation. My question is that
Wycliffe, we cannot hear you. Mr. Wycliffe, sorry, I think you're having a bit of network issues on your side. I'm kindly requesting perhaps you can type your question in the chat. I'll read it out. So as we wait for Mr. Wycliffe's question in the chat. Sorry, Mr. Wycliffe, we cannot hear you. I think you have some bit of connection issues on your side.
My question is about the 6.
Is it okay? Is it okay if you put it in the chat box? Then I can just read it out. Okay, Mr. Wycliffe, we've lost him. So let me just go right to the next question here in the chat. We have a question from Mr. James. Mr. James is asking, what is the meaning of percentage RSS activation, opening of the pads? That is Mr. James's question. Over to you, engineer.
Okay, yes, so the rotary steerable, like the name, it's steer while rotating, right? So there's a percentage of steering which is 0%, mean neutral. That means it's not doing anything, it's not deflecting. And then 100% steering means it's deflecting in the one direction, in that direction 100% of the time. So 100% of the time means what? So the tool have a cycle. So let's say 3-minute cycle. So if I say I want 50% activation only, so in the 3-minute cycle, it will steer for 1.5 minutes and then go neutral for 1.5 minutes. But if I say 100% activation, in that 3-minute cycle, it will be steering all the time. So steering means it point in one direction, which is defined by whatever the DD is trying to achieve, and then it deflects the tool all the time in that direction.
Okay,
so that's what.
Thank you. Thank you. I believe that was well clarified for Mr. James. The next question, okay. Mr. Wycliffe has dropped in his question in the chat. Let me just read it out since we had. Okay, Mr. Wycliffe says, okay, this is Gideon. Sorry about that. Gideon, if you've picked Mr. Wycliffe's question, you can ask it, but I'll proceed with the current questions that we have here at the moment. The next question is from Tadeo. Tadeo is asking, are wells in Tilenga high inclination angle? Because the dog leg is very high. So I think, engineer, you can summarize for him on that.
Yes, 75% of our wells end with more than 75 degrees. So they are considered high angle. Yes, almost all of them. Yes.
Thank you. Then the next one is from, okay, this is an anonymous attendee. The next question will be from Ebenezer. Ebenezer is asking, what is SAG in full?
SLG?
SAG, that's what she typed. I think perhaps it was an error.
Maybe he wanted to type SAG.
Yeah, SAG.
Yeah, it's the SAG. Okay.
Yeah.
So this, yeah, the SAG is a correction for BHA misalignment. So you have your BHA in the hole, it's 6 3/4 in a 10-inch hole. It's not going to sit perfectly in the middle. So based on the stabilizer where it's sitting, there's what we call the sag. It will be touching somewhere. So we need to correct for that misalignment. So that's what we call sag, S-A-G, yes.
Thank you. Then the next one is what is magnetization of the drill string and what is the impact on surveys stroke drilling?
Correct. So if you get, and so when you are drilling, you could get either a, what you call a hotspot on your tools, which would mean you get a magnetic spot there, which would affect the reading from the MWG, because the MWG, it reads a magnetic field and then it derives an azimuth. So if you have an external magnetic field that's affecting it, then the readings would not be accurate. So it will give you wrong azimuth, basically. So if, for example, if you have a mud that have some magnetic particles, then they will affect the readings of the MWG when it's reading the azimuth. So it will show you that it will give you the wrong azimuth, basically, right? And so if you have a wrong azimuth and then you cannot match the criteria, then that means you are going to you're not going to go in the direction where you think you are going. Yeah.
Then thank you on that. The next one is why do you say a motor BHA cannot transmit weight at such a small diameter?
Okay, and it wasn't about the diameter, it's at such a length, at that ERG ratio. When you the deeper you go, then you need to rotate before you transmit any weight. So if you are trying to drill that whole size at that depth, with a motor, you because you don't have the vertical weight to put the drill collars or something to push, you will not have enough weight to move the pipe. So basically, even now as we drill, even sometimes when we are running down to go and drill, we have to rotate because the pipe by itself would buckle and then they will lay on the low side and then you cannot push it down. So that's it's a known issue for the short radius and very shallow TVD wells. So the solution for that is either you have what we call a push-push machine at the surface to grab the pipe and push. But that was disregarded because it's a waste of, it's more cumbersome and then it's a waste of time. So yeah.
Thank you. Next, we have one about MSA correction. What is MSA correction?
MSA correction is what we call multi-station analysis. So again, so it's still part of the, on top of the IFR, there's a software that's all these drilling companies, Schlumberger, Halliburton, that they sell that you apply, you take a lot of surveys, and then you can do a multi-station analysis and then correct the azimuth. Yes, so it's again one of the corrections you can apply in the survey just to improve. If you do that, then you improve the ellipse of uncertainty. So you get a little bit more accurate measurement. Yeah.
Thank you. Next, we have what is the difference between push and point the bit?
Okay, so the push to the bit is typically where you have the parts. So you have something external. You have parts that are opening and then pushing against the formation to deflect in a different direction. The point, all the point of the bit have an internal deflection mechanism which point the steering unit. Now, the disadvantage of the push is that if you have a washout, then your part will open, but you are not going to push because the hole is now big hole. That's why we in this for the Tilenga, since we knew that we were going to get washout, we couldn't go for the push to the bit. So we went for a combination of push and point because this one push internally, so it's not sensitive to the watch. It's not so sensitive to the external washout because you still deflect it. So that's what we call this a hybrid push and point, right?
Thank you. Then we have another one from Mr. Isaac. Mr. Isaac is saying, how does a reduction in lateral and high side uncertainties improve the overall collision avoidance strategy in the deep sections, that is intermediate and reservoir sections of the wells? Then additionally, could you explain the impact of using the GWDN90 and gyro at TD on these uncertainties?
Okay, so the first question, how does that reduce so the deeper you drill, the bigger your ellipse will become, right? So for example, if I drill a wells at 1,000 kilometers, then wherever I am, I will have an ellipse that's, let me take a number. Let's have a circle of, let's say, 11 meters. If I drill to 2,000 meters, that ellipse keep growing bigger. So by the time I get to 2,000, the ellipse will be probably 20 meters. So it will mean that any wells that come in the vicinity of that 20 meters, I'm not going to be able to drill because I'm showing that I could be touching those wells. So that's why if you, the more you reduce that ellipse, then you can place the wells, you can come close in close proximity, even with the own well that you are drilling, because remember we drilled those wells 2,000 meters. So when they are parallel at 2,000 meters, it shows that the ellipse are started to get close. So that's define the limit where you can go. So that's why the ellipse, by reducing the ellipse, then you can not only place them well, but it allows you to fine-tune your collision approach, because you can get them closer if you want to. You don't have to separate them if there's no need for. And the GWD, again, so same thing. Now we have three holes. We have the top hole, the intermediate, and the reservoir. When you drill the top hole with the GWD had a beta ellipse of uncertainty. So when I set my 10 3/4, the ellipses are very small because the GWD is better than the MWD data because it's not affected by any magnetic interference. So I'm starting already with a reduced ellipse compared to if I had no GWD, even if I had no other well, if I had no GWD, I would have started drilling the top hole, the intermediate hole with a bigger ellipse. And the deeper I go, the ellipse will keep growing. So anytime you can reduce the ellipse at any point of time, it's always good. Yeah.
Thank you. Another one, more or less the same like that from Mr. Gerard. Gerard says, could you elaborate on the reason for not fully utilizing GWDN90 or the gyro at TD, which could actually give the best uncertainty of 7, as elaborated in the presentation? That is Gerard's question.
Yes. Correct. So GWD90, there was 2 reasons. So if you look at this chart that I show here, the reason why I highlighted the GWD90 in yellow is because GWD90 was going to give you the best uncertainty, correct? So you have 2.5 meters of ellipse less. But if you take the cost, what it would take you to have the GWD, it wasn't available at the tender process. Plus, if you take the cost of that, it would almost double the cost of your well versus the reward that you are getting for 2.5 meters. Does that make sense?
Thank you. Thank you. Then we have one from Mr. Ivan saying, consider a scenario that we encountered a tight spot. What could be the maximum number of bottoms up and the circulation time before deciding to backrim, considering that we used maximum design saturation parameters?
Okay, so that's very interesting question, because that's something that we still actually working on it. So when you get a tight spot, the first thing is what's the source of the tight spot? Is it a formation collapse, maybe a wall bore stability because the mud weight is not adequate, or is it because you have a lot of cuttings in the hole that you didn't clean? So you have to first of all to define in which window you are falling. If it's a well bore stability issue, then the problem you need to increase your mud weight to be able to hold the well, intact. Otherwise, you keep getting the tight spot. If it's a hole cleaning issue, usually we do for this well 3 to 4 bottoms up, or until you get shaker cleans. Now, depending on the well profile, the bottoms up could be deceiving. You could do 3 bottoms up and then you get no cuttings at surface and you think your hole is clean. But it's probably just an indication that all your cuttings are laid in the horizontal part or in the slant section somewhere. So again, it's profile dependent. You have to understand, and that's why the use of technology like a coating flow machine is very welcome. We started the first part with that because you see the amount of coating you are getting out, and it tells you that you still have this amount of coating back in the hole. So if it's a hole cleaning issue, then you need to continue to clean. And if just the circulation is not good enough, then you have to start backrimming, because backrimming is the last resort, because if you move the cuttings, and then you move them out. But you have to be very careful when you backrim, because the BHA could also, while backrimming, you could introduce the formation instability and then start getting some mechanical cavings. So, you know, it's you have to balance the pros and cons before you engage in backrimming. Yes.
Thank you. So let's have three more. We still have quite a number of questions, but let's have three more just to save on the time. Finally, we have the question from Mr. Wycliffe. So Mr. Wycliffe says, isn't the 6 3/4 inch too narrow to accommodate both the artificial lift and sun control equipment?
Correct. Yes, the answer is yes. So, but the design was this is what we call a slim hole technology, right? So we had to go because of the poor pressure regime that we have in Tilenga. You had two choices. Either we had to go for the standard architecture, which is you start with 16 inch, then you set the 13.38, then you drill a 12 and a quarter, then you set the 9.58, and then you drill 8.5. So you see that here we have only two casing size. So again, Tilenga means what we call factory drilling, and then the cost implication. So the slim hole technology was the best compromise of being able to achieve the rate that we still expected to achieve, and then removing one casing size, and then being able to deliver the well in the amount of time that we're given as a target by the atrium. Yeah. So, like, to answer your question, yes, you know, the whole size would dictate how much you can produce, but it's fit actually what the project was designed for. Yeah.
Thank you. Then we've got another one from Mr. Roland. Mr. Roland is here with us today, one of our directors. So his question is, what is dogleg? And what happens if the maximum allowable dogleg is exceeded while drilling?
Correct. Very good question. So the dogleg is the change of inclination or direction. So that's what you see is degree per 30 meters. So for example, if I start from vertical at 0 degree, then if I need 5 degree per 30, that means if, let's say I kick off at 100 meters, then at 130, I will be at 5 degrees. So that means I've changed 5 degree per 30 meters. So it's a combination of both inclination and azimuth change. So I'm simply just talking about the inclination because it's easy to see, right? But the dogleg, if you're having a 3D, is a change of inclination and azimuth within the 30 meters. So now, when you design a trajectory, you design it based on dogleg. You say, okay, here I want to achieve 5 degrees. Here I will do 2 degrees. Here I will do slant. So if I don't achieve my 5 degree per 30 where I'm building, then I'm going to fall behind. I will be below the curve. I will not be at the curve. I will be below it. And then I'll probably not going to land in the reservoir. Or even if I land in the reservoir, I will not land in the with the right angle. Because remember, you have your drain that's given by the geoscience. They say this is where you enter the reservoir, this is where you stop. So it defined already what inclination you need to be when you enter your reservoir. So if I cannot achieve that dogleg, that means I will not be able to land at that angle. So the worst case scenario is, imagine you want to go to 90 and then you don't get it dogleg. What you drill will be vertical, right? So you just keep going down. So that's the worst way of seeing it. Yeah. Hello?
Hello. Thank you so much, Engineer Roger. Actually, we still have quite a number of questions, but this is an indication that the audience has found the presentation as informative and as inspiring, just as I did. Thank you once again for the wonderful responses to all the asked questions. Sorry for those whose questions have not yet been responded to. We are going to compile these questions and we shall have them shared somewhere on one of our platforms, or on the various platforms of ours as SP Uganda section. So please look out for our platforms and try to find this information there. Then I think with the interest of time, I would want to say we are very, very grateful, Engineer Rogel, for the wonderful presentation and for the questions that you've responded to. I believe the audience is still more than interested to engage you, because I can still see a couple of questions coming in, but we shall have a pause on that. And we shall now move to...
If you send me all the questions by tomorrow, I will prepare the answer and then I can send to be shared on the platform. Yeah.
Thank you. Thank you so much for that.
Okay, so I'll stop sharing.
Okay, thank you. So at this point in time is when we move to our next item on the agenda, and we shall now have a brief closing remarks from our SPE Uganda section chair, Mr. Gideon Chibirige. Mr. Gideon, the audience is all yours.
Yes. Can you confirm if you can hear me, please?
Loud and clear.
Wonderful. First of all, I'm just here to extend a very big vote of thanks to you, Roger. In French, we would say un grand merci. Like a very, very, very big thank you to you, Roger, for first of all accepting to take some time off to share with us your brilliance. I must say, I've seen a comment from Ramos that it's an honor to work with Roger. For us here in GSR, every time we hear, we're on the calls and on the meetings and we hear Roger discussing, we're like, oh my God, this is brilliance impersonified. So thank you very much for sharing with us this evening. It's really, really been an honor to have you. And as you can see, this has been a huge success. We have had over 90 participants in this meeting, and I think that just speaks to how hungry people were to listen to you, Roger, and to pick all the insights. So once more from the SP Uganda section, thank you very, very, very much. This has been really, really wonderful, and thank you for taking the time to really let us feed off all your great experience. 29 years is a really, really rich and deep experience. So as you can see on the screen there, the first announcement was to share feedback. Please take time, members, to share feedback and let us know as SP Uganda section how we can serve you better, what kind of topics you would love to see, and we're here to serve you. And to remind you that SPE is the largest global professional organization in the energy industry. So join today. Don't take any other time, because you'll not find anything bigger or more robust than SPE. I would like to end also by recognizing some very, very important people that have been working behind the scenes to make this a success, starting with Miss Yvonne. So Yvonne is actually the one that told me, you know what, in drilling, we have an expert, and the expert is called Roger. So thank you very much, Yvonne Nalinya, drilling engineer on the Tilenga project. Thank you very much for referring me to Roger, and thank you as well again, Roger, for accepting to speak with us. Also, I want to recognize, I think amidst us, we have somewhere on the call, we have Hannah. Hannah designed that poster. That's great work. So this is an engineer. She's with SLB, and she's also designing the poster. So thank you very much, Hannah. Thank you, Chris Person, Communications. We want to also recognize the presence of our directors. We have Director Kato, who is our chair emeritus. Thank you very much. If you've seen this Zoom call, I think you've noticed that he's the one that actually gave us the Zoom access. So thank you very much, Director Kato. Your great service to this nation is very highly appreciated and invaluable. I also want to recognize we had Abed we had Abed, who is one of our directors, on the call as well. We have Roland from SLB. Thank you very much, Roland, for taking the time to attend this. Roland Dombi, he's our director, and he loves SPE, and he's supporting us very well. Thank you so much. And as well, our moderator, Andrew. Thank you very much. He's in the field, but see how we took time running back to the camp and getting to be the moderator. So thank you very much, everyone. And I don't want to take even one more minute than this. I would like to call this meeting to a close. Please look out on all our channels and all our platforms. SP Uganda section, or Society of Petroleum Engineers Uganda section. We have a LinkedIn, we have a YouTube where we're going to post the recording of this lecture so you can go back and revise and learn more and develop more questions and develop a deeper understanding. And we also have many other platforms where we're going to be sharing all this material. Please be a member of Society of Petroleum Engineers. We're here to serve. And thank you very much once again. My name is Gideon Chibirige, chairperson. Have a lovely evening and bye. Thank you.
Okay, thank you very much for attending.
Thank you very much. Thank you, Roger.
Bye-bye.
Bye.
Bye-bye.
Ciao. Bye all.